Okay, so today we go through PCA, which is a fundamental technique for dimensionality reduction. And remember that this is what people will refer to as unsupervised learning, right? Meaning that you get the data is unlabeled, and you just want to learn something about the data regardless of the possible level. Okay, so remember what we've done so far. So we are coming from linear regression, right? So the last topic that we did was linear regression. So we start from there. So from here, we're going to discuss what does it mean to be high dimensional in terms of the data. We're going to do PCA, then we're going to go back to PCA for regression, and then we're going to go to PCA for imputation, because remember in the last lecture we saw imputation. Okay, so you remember how we did imputation for the last class. So let's talk about the interaction terms and the unique parameterization. So let's say we have this data set, right? And this is a data set of taxis versus Uber in NYC. For example, the number of the mileage that you have, the length of the trip, the number of passengers, the time and location, so on. And there is a public data set that has 1.9 million taxi and Uber trips. And each trip is described by a p equal to 23 that are unsellable, okay? So they all come together. And you can see here how the nyc.cab dataset looks like. So you have latitude, longitude, fare amount, the date and time, and so on and so forth. So here we remember that we are doing regression last time, and what we discussed were the interaction terms. And then we started with the simple linear regression model in which we had only the linear term in x1, x2. Then we said, well, if we want to improve the power of the linear regression, what we can do is that we can add polynomial terms and interaction terms. So for the interaction terms, for example, here we could take an x1 times x2 and say that, for example, the fare, right, is well predicted by this linear combination of the 23 features plus some interaction terms, including some noise, right, that corrupts the prediction. And this will be our model, okay? Then let's say that x1 is a binary predictor, and we want to say that x1 is a binary variable that indicates whether we were using a Uber or using a taxi. And let's say that x2 is the length of the trip and y is the fare. And then we discuss how we will interpret B3. Right? And the interpretation of B3 is that we will have a different model, right, for the taxis and for the Uber. And the value of the B3, right, was to change this slope coefficients B2, right, depending on the case, right, depending on whether we're having a taxi or on a Uber. And another thing is that we recall that in order to avoid overfitting, we sometimes elect to exclude the number of terms in the linear model. And the standard practice is to include only the main effects in the model, so that then usually we do linear regression and we look at the sensitivity matrix, which was our x transpose x. We look at the eigenvalue of that object, we see which eigenvalues are close to 0, and so on and so forth. Then one will ask, what do we mean here by main effect, and what makes a main effect important? And you can ask what type of model would it make sense to include in the interaction term without one of the main effects. Okay, so for example, here you see a model on the left in which we have y hat, so the predicted fare is b0 plus b1 x equal to x greater than 13. So in this case, we change the model on the weeks before Christmas, right? So for example, let's say these are the weeks of the year, let's say, and here you have a certain amount of fares closed for the beginning of the year and then for the rest of the year. Or what you can do is that you can also add the interaction term. And here you will have b0 plus b1 plus b2, x2 minus 13, indicator term x greater than 13. So what you do in this case is, again, you go back to this x1 being an indicator function, and you allow your model, you use the interaction term to allow your model for or change in slope depending on the value of the interaction term. And we can ask ourselves how will we parameterize this model. Okay, so it's clear that now we are discussing how we should decide the interaction terms, and how should we decide whether the interaction term is important, and how should we sort of go about selecting an interaction term. And we soon realized that this issue of overfitting, it's really much upon us, because all possible number of interaction terms will be p over p2 factorial, p factorial 2, p over 2 factorial, which is basically polynomial in p. Right? It's a p square. And we can also have three ways interaction. So we can have x1 times x2 times x3. And then, of course, this becomes p cube. And the total number of possible interaction terms, of course, is a summation of all the binomial coefficients. And from the binomial theorem, you know that the sum of all the binomial coefficients is equal to 2 to the p. So considering all possible interaction terms, with all possible order of the interaction term, let's say order 2 or order 3, will be 2 to the power of the number of parameters. And of course, we have 23 parameters, so we have millions and millions of interaction terms. And of course, this goes back to the issue of choosing hyperparameters. So we have a choice of models. The possible ways of including, excluding interaction terms is just a gigantic. So it becomes very, very challenging for us to decide how to build a model with the correct interaction term and selecting the interaction term based on their relevant importance. Okay. So we have a data set of 2 million, right? And the total number of interaction terms is in terms of 8 million. So of course, if we include all possible interaction terms and try to do linear regression on that, then the computation of the solution of the linear regression is never going to come upon us, and the numerical instability will be such that we will never get a meaningful observation. So what can we do? Okay, so we can, for example, subsample the observation. So let's just say 100K observation. And we can try to include all possible interaction terms. So now at least we squeeze the data set to be a skinny and long matrix. But then, of course, we have too many hyperparameters. So we have 8.3 million parameters in our linear regression model with all interaction terms. And we have 100K observations. So we have a severely underdetermined model. So we have many, many different solutions to the linear regression problem, because the number of parameters is larger than the dataset size. And so we cannot identify the problem. Okay, so how do we deal with this in practice? Well, we could increase the number of observations. If we increase the number of observations, then we increase the complexity, so not very nice. We can handpick the interaction terms. We can be like, oh, this variable and these variables that are uncorrelated. We expect one not to influence the other. So we can drop them, but of course then we are adding our bias to the selection of the model, and adding our bias is generally a bad thing to do. And you will soon realize that what you need is to have some other approach to this. And the other approach that you want to take is the dimensionality reduction. And the dimensionality reduction technique, which is most used by people, is PCA, which stands for Principal Component Analysis. Okay? And this is the topic of today, of course. So let's see what we need by big data and high dimensionality. So big data is one of the words that has been abused by the popular media and the popular scientific literature. So now it has lost its original scientific meaning, right? Or engineering meaning. So a way to imagine this is that when we have a data set, we usually represent it as a matrix, and the number of observation n is the number of rows, and the number of predictors or features that we have is p, which is the number of columns. And then you can ask yourself which ratio between n and p gives rise to which problem. Okay, so let's say that n is big and p is small. Okay, so this is the case that we have seen let's say this is mostly the regime in which we have operated so far, right? So we have, let's say we have the usual case that we have, right? So we have the advertisement budget and the sales, and it's easy for us to have many different examples of a certain budget for a certain product for which you have only this limited amount of features, right? Let's say you have an agency, you have an advertisement agency. The advertisement agency has had 10 years of experience, and they boil down the type of budgets that they have allocated to these three features, and you can build the data set there. And we have seen so far that we can generally deal with this problem, right? So this problem is usually pretty reasonable because the number of parameters in the model depends on the number of features generally, and so it is easy to determine reliably a small number of model parameters from a large N. So this is good. So then we can look at the case in which P is big and N is small, and this is generally what happens in, for example, medical applications. Let's say you have a very few people that undergo a certain surgery, or they have a certain condition, right? But for these people, it is easy to observe a lot of to have a lot of observation. Let's say that you have a certain disease, let's say cancer. Of course, cancer. Okay, let's not maybe. Let's say it's a curable cancer. Okay, it's a cancer that doesn't kill anybody. Just a small operation, you're fine. Okay, let's say that you have a very curable cancer, but the type of cancer, it's generally rare, right? So there are many different types of cancer. The rate of cancer in the population is like 10%. So you can imagine that you have a few thousand people that exhibit a certain cancer. But of course, for these people, it is easy for you to have a lot of observations. So for these people, they come in for the surgery, so they stay in the hospital. So you can have a lot of observation for these people, and then you are asked to make a prediction for detecting the cancer, again, benign cancer. And you have a lot of observation, but for very few samples. So this is in nature, this is a different type of problem, right? Because here it's clear that we want to build a model, and we have a lot of features, but we have a very small population. So we cannot reliably estimate our parameters because N is too small. Okay. Now, the case in which we're thinking now is the case in both N and P are both big. Let's say that N and P, let's say they grow linearly together, right? That we have an N equal to a P. So now the first case is that you have a tall and skinny matrix. We said that we like tall and skinny matrices. For P large and N small, we say this is a pathological case. Not much can be done. But when N and P grow big, in a sense, we are balancing between the good scenario and the bad scenario, but we're doing so in a way in which computational complexity dominates performance. Right? So what does it mean, right? What does it mean when N is big? When the sample size is large, there is not much issue from a statistical perspective, and the only issue that we observe is from the computational perspective, because algorithm takes forever to finish. So, for example, if you have a regression model, the matrix inversion is going to take a long time. And so, sorry, but what you can do is that you have enough samples that you can estimate the confidence on your parameters. So you have some extra work to do in order to estimate the confidence that you're doing. And of course, we like to have deep neural networks for these scenarios because we can train neural network efficiently when in large. And basically, the only concern in this case is the computational complexity of the algorithms, let's say. And remember that in general, in the era of large N, we can do a lot of interesting things. We can train a lot of interesting model. But there is the saying, there is the old adage that says crap in, crap out, which is to say that if you do not know what type of model you should select for a problem, it doesn't matter how big N is, you will still do a crappy job in trying to do your prediction task. Okay. When P is big, right, the number of predictors is large, then we have a lot of issues that can occur. So if P is big, as we said, some things are unidentifiable, right? Because you will want to have a model that takes advantage of all the predictors. So the number of parameters in the model has to be sort of proportional to your P. And so you have a lot of parameters to determine from a smaller n. So this problem is not that is underdetermined, right? So you cannot determine all the parameters. There is a lot of correlation between the data. So the collinearity will bring some issue in terms, for example, of the rank of a matrix, right? You could have a lot of linear dependencies between the data, or almost linear dependencies. It makes all the algorithm unstable because the solution, you have a class of solution that performs equally on the data, so that's very nice. And you have the issue of overfitting, right? Because you have a lot of parameters, you have fewer samples, so overfitting is the name of the game. Usually people refer to this situation as high dimensionality, meaning that your problem lives in a very high dimension because the dimension of the problems are determined by P. So usually the label it's fixed to, let's say, size 1, or it's fixed to a smaller size. So the number of features of what determine the dimensionality of the problem. And we can ask ourselves what type of techniques we have learned to deal with high dimensionality. And the answer is so far none. So high dimensionality is a problem when the number of observations is close to the number of features, as we said. And this can also arise if there are a lot of interaction terms, and we try to add the interaction terms to our model. And this brings us back to a previous example. So for example, if we are performing polynomial regression with a high degree and a large number of predictors, when predictors are genomic markers, for example, then in computational biology, you have to consider the interaction terms across genes. So the interaction terms are actually physically motivated. We are not adding them to the problem in order to improve our predictability, but they are actually baked into the physics, into the fundamentals of the product. And for example, when the predictors are count of the English word appearing in the text, again, the English vocabulary has around 6,000 words. So there is no way in which you can actually choose a lower dimensionality of the problem, because the statistics of the word could have a support of around 6,000 words. So it is not your choice. Okay, so just we can skip this one here. We can discuss about multicollinearity, right? So you can observe multicollinearity when you look at the linear regression, right? So for example, yeah, so you can see this example. So a couple of slides on sklearn that you can look at. And now we can focus instead of a more fundamental setting that will bring us to PCR. So let's say that we have a certain set of observations from Z1 to Zm, and we just try to predict Zi. Okay. And so we have in order to predict Zi, we take the summation of the xj's, and we have the parameters phi ji for some fixed constant phi j. So what we can do is that we can choose then the Zi's as intermediate predictors for our label y, so that then we can build the predictor y as a linear combination of the Zm of the Z's, and the Z's have much lower dimensionality. Okay, so we start with an original set of feature of dimensionality p. We choose an intermediate set of features of dimension m, and then we build our label out of the m predictor Z's, so that we have reduced the problem from dimensionality p to dimensionality m. And the way in which we have we have generated the Z's from X, let's say that are fixed and constant, right? So as a first approach, you can imagine that for this phi ji, you just choose some random numbers. So you say, oh, well, I don't know anything about this data, so I just choose a random combination of the ZJs in order to do my prediction. This is something that you could build. But now we have, if we want to set the problem more formally, we will say, well, if you have m predictors that you can obtain as a linear combination of your p original features, How would you choose the linear combination optimally? And optimal in this case will be so that the ZM are good representatives of the higher data, of higher dimensional data, X the dimension P. And the idea is that, of course, the way of determining these coefficients could depend on the application, and this is very undesirable, right? Because sometimes you will want to spend the time determining a good set of ZM in a way which is agnostic from the downstream task, okay? So let's say, again, let's go back to the data set of taxi rides. It is, let's say that somebody gives us a job at Uber, and our job at Uber is to, let's say, to perform some prediction on the app, to do some dynamic pricing for the taxi ride of Uber in certain areas of New York. Of course, our job is not going to be one job, right? Every day, our boss is going to come in. It's like, oh, try this idea, try that idea, try that idea. And so I really don't want to have on my hard disk 2 gigabytes of data of rides. And every time the boss gives me a task, I'll go and I do a dimensionality reduction from 8 million interaction terms over a data set of 1 million of 2 million entries into some lower dimensional subset of Z's in which I can do the job of the day. I would like to do the following, right? I would like to have a good representation of my whole data in terms of the Z's, and just do my daily job on the reduced dimensional Z. I would like to have an approach in which I say, well, I can choose first a measure of closeness between the X's and the Z. I can generate a much smaller data set. Instead of having dimension of trillions as dimension of a few 100,000, I keep that reduced data set on my computer, and every day I do my job on this reduced set. Okay. So we have the idea that we want to go from a high dimensional space to a lower dimensional space in a way that preserves some properties between the high dimensional space and the low dimensional space. And then these properties do not depend on the downstream task. And of course, we want to do this in a smart way, because we cannot go and try to do some search over the parameter space of the 5Js. Okay, so here PCA comes into mind. So the idea is that if somebody gives us this high-dimensional data here, which a high dimensional in this case means two-dimensional, what I can do, right, I can try to look for a set of components over which to project the data, so that most of the information on the data is preserved. Okay, so let's start here from a completely intuitive aspect, right? So you have this cloud of points, and somebody tells you, oh, this point is too high, is to the high dimension. It is in 2 dimensions. I would like you to give me a representation of these points into 1 dimension. Okay. So of course you notice that most of the spread of the data occurs around this, let's say, 45-degree line, right, along this diagonal. So you say, well, if I project my points along this direction, I have the highest likelihood of distinguishing 2 points in the original dataset. Okay, so in a sense, I'm looking for the projection from 2 dimension to 1 dimension, which is the most informative one. Okay. Then, of course, once you choose this dimension to be your principal dimension, let's say that you do not want to, you want to express this as a one-to-one transformation, so that you know how to manipulate the data in a way that is lossless, right? So you don't lose information. Then you say, well, if I choose this as my principal component, as the direction over which I want to project the data, then I can choose the orthogonal component, so that now I have a two-dimensional transformation. I go from the 2-dimensional space to another 2-dimensional space, and I know that my first coordinate is going to be the most informative, and I have the second coordinate, which is the least informative. So if my boss tells me that I can have an NVIDIA GPU and a ton of RAM memory, then I keep the 2 components. And if I'm forced to downscale my dataset, I know that I just need to throw away the second component. Okay. So the need of identifying the components over which most of the information lies is sort of hierarchical, right? So I choose dimensions, and over each dimension, I try to keep the most information. And as I go down over my coordinate, I lose information. Okay, so here I will identify this diagonal as my first component, and we will call it the first principal component, and this one here is the second dimensional component. Okay, so now remember that things are easy here because the dimensionality reduction is from 2 dimension to 1 dimension, but of course that's because we don't have 4D displays. Otherwise, I will show you this in 4D displays, and you will see that my objective is to have a one-to-one transformation of the data in which I choose a successive set of orthogonal directions, and I focus in squeezing most of the information on the different components in a way that as the component goes down, then the least variability in the data is represented by the component. Okay, very nice. So this is the intuitive idea. Let's try to put it more in mathematical terms. So let's say that we say that PCA, which again stands for principal component analysis, produces a list of principal components from Z1 to Zp, such that Zi's are a linear combination of the original predictor, and it's a vector of norm 1. The Zi's are pairwise orthogonal, and the Zi's are ordered in decreasing, they're ordered in decreasing order of the amount of information captured about the data. Okay? There is, the observed data shows more variance in the direction of the Z1 than in the direction of Z2, in the direction of Z3, and so on and so on and so forth. And to perform dimensionality reduction, we select the top n principal components of the PCA and throw away the other p minus n components, and claim that these predictors are the best predictors that I can use if I'm forced to reduce my dimension from p to m. Okay, very good. So the idea is, again, that we have to choose this component so that we capture the most variability of the data, and then we remove this component from the data, and then we repeat the observation with the error that is left after I remove the first component. Okay, good. So now what does it mean to have the most variability, right? So the term at the beginning seems a little bit unclear, but it's clear. The term is unclear, but we can now try to represent the variability in terms of some sort of energy, some sort of variance of the data. Okay, so let's go back to the previous data set. So what we can do is that we consider the projection of the points along this principal component. So you see here that you have the different element in the data set. Of course, they are subsample from the previous figure here. That's not a problem, just so that we don't have a cloud of points and we cannot understand anything. So what we do is that we subsample these points just for representation, and then we can see the error, we can define the error between the projection over the first principal component and the original data as this beautiful vector. So this vector here is the distance vector between the first principal component and the true data in the dimension p. So the dimension p here is 2. The principal component is a line, so it says dimension 1, so that you see the projection that you obtain is a point along a line, right? So the projection you obtain is a simple scalar, and the original point is in 2D. So the distance between the point and this hyperplane and this principal component is measured along the orthogonal direction. So let me use a high dimensional terminology. Let me call this as a hyperplane. Okay, so the green one here, I will define it. I will call it as a hyperplane, because in my mind this object is a high dimensional object, and I will say that the distance between the point and the hyperplane is along the orthogonal direction of the hyperplane. Okay, so then now we can measure the error in the projection of this data set along this hyperplane as the sum, right, of the norm of the vectors that measure the distance between the point and the projection. So it's clear that our interest is in choosing this direction so that this residual is minimized. Very nice. Okay, very good. So this is again the intuition that we have. So what is the method behind this? So PCA is a well-known result from linear algebra. So let Z be the n times P matrix, consists of the columns of Z1 to Zp. And then X is the n time P matrix of Z1 to Zp, which is the original data. Then, of course, we can normalize the data to zero, to mean 0 and variance 1. So we just assume the usual normalization of the data, so that we know that the data is centered in the origin of the plane, and the variance is normalized to 1. These are just let's say P plus 1 parameters, nothing to worry about with respect to our n times P parameter. Then the matrix omega is a P times P matrix, whose columns are the eigenvector of the square matrix X transpose X. So that we can say that Z n times P is equal to X n times P omega P plus P. So this omega, right, is a projection from, the data here is n times P. This omega is a change of base, right? You can say that I have the original points, which are this n time P matrix, and I do this transformation omega to obtain another representation, another set of features, which are again n times P. So this omega times omega has this feeling of a geometric transformation, because the omega is a square matrix. And you can think that what this matrix does, takes one vector, right? It takes each data entry from let's say the standard basis in the Euclidean space of dimension P to some other basis, which is determined by omega. And then we can ask ourselves which transformation we should take in order to, again, minimize this the power of the residuals at each coordinate. And it turns out that we should choose the omega, so that the columns of omega are the eigenvectors of the square matrix X transpose T. Okay, so we're going to see this in a second. So it's always, of course, there are plenty of packages to do PCA, but you should try it by yourself. And again, this X transpose X, now you should, after doing linear regression and doing the sensitivity, you should understand this as being the sensitivity matrix of your data. So how would you do, and how would you go and implement PCA by yourself as you implemented linear regression by yourself? So you start with your data. Always remember to standardize to mean 0 and variance 1. The variance 1, you can let it slide, because the variance 1 is just a multiplication by the scalar, but the mean 0 is very important, okay? Because this omega transformation is going to be a combination of a rotation, an ablation, or whatever. However you understand a linear transformation on a Euclidean space to be. And the point is that if you don't start from mean 0, right, the transformation is gonna move your mean from the original mean to some other mean, so that you lose sort of the invariance of the mean, right? So if you start with mean 0, so that the average of data is in 0, you hit the all 0 vector with omega, then you're going to get the all 0 vector, so that the transformation that you do doesn't change the mean of the data, because the all 0 vector is invariant with respect to the transformation. If you don't normalize to the mean, then the mean is going to move around for different choices of omega. Okay, so just remember to always put the mean to 0. So what you do is that you normalize the data, mean 0 and variance 1, and then you calculate the eigenvectors of X transpose X, and then you extract this eigenvector, and you're going to have P eigenvectors that are orthogonal and norm 1. So you stack them all together, you create omega, and then you just do a matrix multiplication, Z equal to X times omega. Of course, this is not an efficient way to do this, because you should have understood by now that calculating eigenvalues and eigenvectors is not an easy business. You should use some decomposition, some QR decomposition, some householder projection, some Cholesky decomposition, but this is something that you can see in some other numerical analysis course. But of course, nowadays we don't do this ourselves. We just use the PCA, the decomposition.pca package in sklearn. Okay, so let's go back to this example of a heart disease, age, REST BP, cholesterol, MASH XR. So you decide to do PCA.fit over X. This will give you the 4 components, right? So we start with 4 features. We obtain 4 components. And as you can imagine, the 4 components are ordered from the largest eigenvalue to the smallest eigenvalue. Okay. Very good. So if you do this experiment, right, you will get the eigenvalues ordered like this, and then you will get the components, right? So they will tell you what are the components, and then they will tell you the explained variance. Okay. So if you normalize the variance of the data to 1, then this explained variance will tell you which portion of the data variability is contained in each of the PCA dimension. This is very intuitive, right? So if you have the cloud of points, and this cloud of points is variant 1, you are rotating and you are rotating and you're doing a fine transformation of these points so that you are aligning the largest variability with each of the axes of your Euclidean space of P. So what you do is that you for each of the components, let's say X, Y, Z, K, you try to push the largest variability in that component, and the variability decreases as the coordinate index increases. So here is saying that the first component contains 75% of the variance of the data. Okay, so already just by using one component, you can explain 75% of the variability of the points, so the variance of the points that you observe. Then you go 15%, so the second component already does a great job. And you can see that the other components, they just express something below the 10% of the variability, right? So the PCA components really capture the largest variability in the highest components, and the lowest components, you can sort of disregard them easily because they don't explain much of the data that you observe. Of course, always remember that this is with respect, this is irrespective of the task, right? So here you just say, well, if I reduce the dimension from 4 to 2, I can maintain, let's say, 90% of my variability, right? 74 plus 15. So 90% of my variability is explained, but this is irrespective of the final task. So never forget that maybe there is some PCA component that very strongly correlates to some downstream task, right? So let's say to predict again if the person has some heart defect, right? Maybe there is some precise linear combination of the data that will be able to explain to predict heart condition, a certain heart condition very precisely. And this is not preserved by PCA, because PCA is, again, an unsupervised learning approach. You just say, well, I just look at the variance of the data, which is sort of a Euclidean, is a linear measure of variability. And I say, under this assumption that minimizing the loss of variability in terms of variance, in terms of power, in terms of L2 norm, it's a good job. Of course, doesn't mean that it's a good job for all possible downstream tasks, but in general, it's a principle that you can adopt if you don't have reason to believe that there is some specific non-linear relationship between your label and your data. Okay, so don't forget that when you do PCA, you're losing information, and if this information is only corresponding to a small percentage of the variability of the data, nonetheless, this variability is only measured in linear terms, and there could be many nonlinear terms that are lost by PCA. Okay, moving on. So we have our random variables, our 4 features, and we decompose them in 4 PCA components. And then the beauty is that if we just pick the first 2 PCA components, then what you can do is that you can have a 2D representation. Okay, never underestimate 2D representation, because having 2 eyes, 2D representation is the most amount of information that we can observe. You can absorb through our eyes until we have 3D displays, but we're still not there. So here we go back and we plot the projection of the 4-dimensional points in the 2-dimensional projection and the 2-dimensional directions corresponding to the first 2 PCA components. And we notice here that we can go and also color the points according to the label. And we see very well that these two PCA components, they are telling us a story, right? They are telling us that the people that are the heart disease are represented in this, let's say, half plane, right? They are well represented in this half plane. The people that no heart disease are represented in this half plane. And we see that here there is a clear sort of separation, right? In which you can have a certain confidence that if you are at the right of this hyperplane, then you might have a heart disease. If you are left of this, you might not have a heart disease. Okay, so what we were able to do, right, is to gain a visual insight, right, on the organization of the data by using the PCA components. And this is something that some of you already did in your project, maybe knowing or not knowing what were the basis for this, But it's clear that since it's hard to observe for us to observe pattern, projecting the data over these two informative dimensions makes it possible for us to observe patterns that otherwise we will not be able to observe in some higher dimensional data. Okay. Okay, very good. So let's take a short break. Let's take a break of 10 minutes. I'll see you back at 8:30. And then if there is any question, you ask me in chat. Otherwise, I'll see you in 10 minutes, okay? We do another hour, 45 minutes, and I'll let you guys go back to study for your midterms, okay? Okay, guys, any questions before we go ahead? Yeah, remember to let me know if you're looking for any internship. There are a few opportunities that I know about. Yeah. Of course, you have to run the 50K marathon before I consider your CP, but it's not a problem. Okay, good. So we discussed PCA. Let's discuss PCA for regression now. So how we're going to use this PCR. So PCA is easy to use in Python, and we can then pipe it with regression, as we said. So then if we use all the P's of the new ZJ, then we cannot have an improvement of sort, right? But what we can do is that we can select the first M components of the PCA and then use this for the prediction model so that we've done a reduction of complexity from P to M. I ask you to believe me, right? That finding the closed form solution for the PCA components in terms of eigenvectors and eigenvalues, it is numerically easier to obtain than finding the linear regression solution for the linear regression closed form solution by considering that, let's say, a certain amount of interaction terms, right? So they both of these tasks, they involve minimizing some L2 norm, clearly. But PCA considers the X transpose X. So it's a P times P type of P times P type of matrix, and so it can be approached using some iterative terms. As we said, this QR decomposition type of approach, and this is easier than the matrix inversion, which is involved in the linear regression solution. So the complexity is on our side. And then remember that the PCA results, right? The PCA transformation is generally more useful because it can be pipelined to more downstream tasks than the parameters of the linear regression model. Okay, so when you have a linear regression model, then those parameters are the one of the model that you use. But if you have a PCA decomposition representation of the data, then you can use it for regression, for prediction, for many different downstream tasks. Okay, good. Okay, so we're back here, right? So we did the PCA on our data. We went from P to M. Of course, we have now the hyperparameter M, and we always say, right, that choosing the optimal hyperparameter is just as hard as solving the original problem. So now the idea is that how we're going to choose M in order to have the best performance that we can for the complexity that is allowed by our algorithm. Of course, this is an art, right? So how can we check what how can we check the performance for M? What we can do, and we should always try to do if we have enough data, is to do cross-validation. Okay. So you want to use cross-validation for this. So remember that PCA is an unsupervised learning algorithm, meaning that it's independent from the outcome variable. So we just do PCA on the data. We don't consider PCA on the label. PCA is not good in the sense that it's hard to give direct interpretation of the coefficient of a PCA. So if you want to reflect, it's like it's a two-stage algorithm, right? So if you do linear regression, then you know that you can look at the coefficients of the linear regression and understand how relevant is a certain feature to the prediction. Now, let's say that you have PCA. Now, the PCA is a linear combination of the original features. So what you can do is that you can consider the product of your linear regression over the PCA component, so that the PCR coefficients, and you can multiply by the coefficients in that form the certain PCA component. But then, on all these passages, you're losing interpretability, right? Because it is not clear how to validate the relevance of a PCA components if the PCA component does not uniquely represent, it's not uniquely focused on a specific variable. Often you don't improve the predictability of the model. Of course, PCA generally reduces the amount of information available. So when you do PCA, if you see some improvement on the performance of the model, it just comes from complexity consideration, from numerical instability. But what is PCA great for? For reducing the dimensionality of the high dimensional setting. So going from 1 million dimension down to a few hundreds, visualizing the predictive features and the response, especially in classification setting. So you can, as we said, take a PCA decomposition down to 2 components and visualize the projection of the high dimensional points and their label. And also, it's also useful for reducing multicollinearity. Okay, so since the PCA components are independent, are orthogonal by construction, then there is no collinearity between the PCA components. So if you are doing a regression over the PCA components, then you don't have to worry about multicollinearity, and this usually improves the computational performance. Okay, good. So you can do some interpretation of the terms, but you have to be careful. The estimate of a coefficient of a PCR is distributed across the predictor through the associated components, and it can be transformed back to the prediction of the original variable. So here, let's continue on the data set of heart attack. Okay, so here you have the different PCA components. Okay. And the last one is the linear component. Okay, then we can see that how the different PCA components are formed. So since the PCA components have power 1, right? So their magnitude is relatively, it's between 0 and 1 basically. And here, what do we plot, right? So this is the coefficients of age, sex, chest pain, and blah blah blah. This is how they are obtained in the different PCA components, and this is how it's obtained the linear regression. For example, here we are saying, right, that PCA7, right, is formed by a linear combination of the ECG, the FBS, I don't remember, and the cholesterol, right? PCA6 has a negative contribution from the REST ECG, a positive contribution from the cholesterol, and a positive contribution from the FBS. And you see how each PCA component is obtained. And it's clear that it's not that clear, but basically the second PCA component is focused mostly on the REST BP and so on and so forth. So here you plot the composition of the different PCA components as a linear combination of the original features. And in the last one, right, you obtain the linear combination coefficients from the linear combination. And this gives you an idea on how the prediction values the different coefficients for different PCA components. And you see here that the PCA, no PCA components represent this data. Okay, so this is kind of confusing. But here, the features are not standardized, right? So if we standardize the feature, we actually see a different story, right? So you see that all the different PCA components contain a linear combination of the different features as after standardization. And you see that the PCA7, right, it's very much a good predictor for whether the person has a heart attack or not, okay? So remember that these components are just created in order to represent the variability of the data. So they are uncorrelated from the label. So the fact that the PCA component that has, let's say, low explainability, low representability of the variance of the data is very much correlated to the label is not surprising to us, because we understand that this representation is unsupervised. So it's done with irrespective of the downstream task. Very good. Okay, so let's dig a little bit on the underlying mechanism. As we said, PCA seeks to explain the data by finding the direction which explains the greatest variance. Variance works well because centering is inherent in the formula, right? So it turns out that finding the larger eigenvalues of a sample variance matrix and then projective iteratively accomplishes this task. Okay, so this is how you understand projection. Okay, so as we said, we pick a dimension and we pick the distance between the certain direction and the data. So you see here that the issue is that the data is not centered. This is what we were saying before, right? The center is fundamental. So when you calculate the error, you get a large error here. And this is undesirable, right? Because if the data was centered, then the variability would be different. So then, so this is in 2D, right? In 3D, this is what happens, right? So this is your axis. This is the original data. So what you do is that you project first on the first component. So you see the residual on the, so here we are projecting over this green, red, and blue components. Okay, so these are the eigenvector of the X transpose X. So the original data is this. After the first projection, we have projected along the first eigenvalue direction. So now we are in the red and green hyperplane. And then this is a two-dimensional, 2D space. And then you project again over the third component, and this is we're going to go from 1D. Okay, so the repeated projection, you go from 3D to 2D, from 2D to 1D. Very good. So although PCA works by iteratively moving the eigenvector with the largest variance, in practice, we do the exact opposite to perform dimensional reduction. So we find the dimension with the most variance. So by finding the dimension with the most variance, we can do things like keep the fewest dimension that retains 90% of the information. Okay, so what you do is that you try to retain information and instead of removing variability. Okay, so you do this. Okay, so now let's go back to the problem of imputation as we discussed last week. So remember the imputation and how we discuss imputation. So we said so we have an x1 and x2 variables, and let's say that we have a larger data set, and so sometimes we have some entries that miss the x1 and x2. So what we were doing at the point is that we imputed x1 and x2 to the mean, for example, and we said that if we do this, we introduce some patterns in the data that wasn't originally there, and this is the example that you have, right? So this is a larger data set, the x1 and x2 are missing for some of the points. We impute the two of them, right? We get this cross appearing, right? We get this hyperplane, this constant values appearing, right? So here we have imputed x1 to the mean, and x2 is the true data. Here we have the x2 that is imputed to the mean, and the x1 is true. And then in the x1 mean, x2 mean, we have points in which we have imputed both the coordinate x1 and x2. Of course, this is not very nice, right? Because this pattern can produce hallucination in our inference, in our downstream task. So let's see that. Let's see if we can use PCA to work on imputation. So we want imputation to take advantage of the relationship between predictors, imputing missing values in one predictor using the values of the others. So that we said that this is the most advanced imputation method when you do not just impute to the mean, but you use a certain model to do imputation, right? So you train the imputation model, and then you impute using this model. And of course, if you have multiple imputed values over the same data set, you have to train multiple models. This, of course, becomes a mess. So because when we have many predictors, the observation I and j has similar values for most of them, but j is missing the predictor in Q, we impute using the i's values for P. So if we find two entries that are close, and we just translate the values from one to the other. So in other words, we want the imputation to take into account the links between the variables and the global similarity between the observation. And this is the idea behind the iterative PCA algorithm for imputation. Let's see how it's done. So we start with this very simple data set of x1, x2, and we say the x1, the data set entry 1 has a missing in x2. So what do? We initialize by imputing to the mean for any reasonable value to do so. So we go through these values, we find that 0, 2 is the mean, we impute there. Very good. That's the first step. Next step, right? We perform PCA in the data set on the data, including the imputed value. And then we project on the first PCA component. Okay. So here, this is the data set. We have imputed everything, and we have projected stuff down. This is the imputed value, and this is the projection of the imputed value. Okay, what's going on here? Good. Then, using the projection value for the missing predictor, we use to update our imputation. Okay, so this is the first PCA component. This is the imputation, and this is the imputation update, right? So we said, well, this would have been the imputed value over this missing. Okay. Then we repeat this operation multiple times, and we keep repeating the following, right? So this is when we predict the value here on the x1 variable only. Here we do the PCA. Here we look at the x1 coordinate of the projected value, and we update the current imputation with that value. Then we go back, and basically, since we changed the imputation, now we can redo the PCA with the new value, and we can keep the operation. And we will say now, well, I have this new imputed point. I do the PCA from this new imputation. I get a projection of the PCA components, and for this projection, I update again the point, and I keep repeating this until I get to the point in which there is no more update in our imputation value. And what is that we obtain in this way? We're going to see next. So first, let's see the recap of the procedure. So we initialize by the imputation with some reasonable value that is to the mean. And then we iterate until convergence the following. You perform PCA components on the complete data. You retain the first n components. In this case, it was m equal to 1 because we're only in 2 dimensions, so we don't have much to project. Then we project the imputation back into the PCA space. Then we update the imputation using the projection value. And then the question comes, so well, how should I choose my M in my PCA iteration here in order to have, let's say, some reasonable behavior of this? Of course, we want to use cross-validation. We want to use different M and see which M gives the best imputation. In practice, this often refers to overfitting, especially if the matrix is sparse with missing value. So sometimes you use some regularized PCA approach that shrinks the singular values as you make the updates. Okay. So good. Yeah. So it should be clear to you that basically the point at which you converge is the point in which the PCA of the original data, right, is not affected by your imputation. And what is the reasoning behind this, right? So if you have some reasonable data, some original data, and you do PCA on this, you're saying that the data lives well in this lower dimensional space. And when you add some imputation value, you will want this imputation value not to alter the PCA from what it was originally, from what the original behavior would have been, right? Because basically you want to say that if a lower dimensional representation of the point existed for this original data, the imputed value should not change the geometry of this low dimensional representation. Okay, so this is the procedure that you're doing. Okay, very good. So now let's see a different interpretation of PCA. So one interpretation of PCA that we've seen so far is this idea of capturing the variability of the predictor. And as you said, an alternative interpretation is the one in which you find the low-dimensional linear surface, which is closest to the data points. Okay, so here we're very brave, right? We are representing the data in 3-dimensional points, and we are saying that we look at the 2-dimensional space. So we look for the 2 largest PCA components, so that the distance between the points and the surface is minimized. Let's discuss matrix completion now. Another, I think we saw this when there was the student presentation on the Netflix. Oh, it was Netflix. Yeah, it was the Netflix data set. When we said, oh, let's say that we have a matrix where we have the users and the rankings, or the way which we can provide a prediction of the ranking of a certain user for a movie that he hasn't seen yet. This translates to a matrix completion problem. Okay. So matrix completion is another application for which PCA is suitable for imputing data that are missing around. And this is part of the recommendation system, let's say, literature. So let's say that we have again an n times p matrix for the movie ratings in the Netflix customers, where n is the number of customers and p is the number of movies. The data contains missing entries because some people didn't have the chance to see some movies. We have no reason to believe that people have specific reason to not watching some movies. Okay, maybe. There are some imputation to be done there by over some latent variable that we have no access to. And when we do matrix completion, we are imputing missing values, which is equivalent of predicting which ranking a certain customer will give to a movie if they watch it. And, the textbook is here. Okay. And this is where you will use PCA. So you will do the PCA components, and then you will reconstruct the missing as using the PCA decomposition. Very good. Let's see if there is any question about this. Any question? Tom. Otherwise, I load up something easy, something else easy. Okay. Let's go to the next one. Okay, then we move to the next topic. If there is no question, maybe we're going to move toward logistic regression finally, since I think many people are waiting for logistic regression. So let me just open the set of slides. Bye. What is it? I cannot do full screen mode. Why I cannot do full screen mode? Full screen mode. Okay, good. Let me share it again. Good. Logistic regression. Here we go. So introduction to classification. Why not linear regression? Binary response resolution, logistic regression. I think this presentation will answer some of the questions regarding the challenge from last time. Okay. So far we focus mostly on regression problems, but of course you guys know about classification. Okay, so let's go back to our advertising data sets with the budget that we always look, and observation predictors, and then the outcome variable it was continuous. Then we go to the heart data set, and we see here that we have the sex, chest pain, cholesterol, HCG, and so on and so forth. But what we're doing is that we are predicting now a response variable on whether the person had a heart attack, and this was a binary answer, was yes or no. So yes indicates the presence of a heart disease, no means no heart disease, and now we have we have 13 predictors, right? And we have to predict a binary output. This brings us to the difference between quantitative and qualitative variables, right? Before we were discussing quantitative variables, so some quantity that had an idea of continuity, right? So the number of taxis, number of pickups, and the number of bike rentals, the budget, so that even if, of course, the problem is somewhat discrete in nature. For example, the number of taxis can only be an integer. The amount of money that you're paid in dollars goes up to the cents. You cannot be paid a lower fraction. But there was an idea of continuity, right? So that if you predicted the taxi pickup is 1.34567515, so on and so forth, even if this is a continuous number, the closeness between this continuous number to the integer that was the physically possible label for this variable had a sense. Okay? This is very different if you have a categorical variable or a qualitative variable, where you said whether you're, for example, a student or a worker, right? So you cannot predict that the person is a certain fraction of a student, a certain fraction of a worker, right? So this doesn't really make sense, right? Or if you are, let's say, certain ethnicity, right? Of course, you can argue that maybe there is some meaning of continuity between the two states, right? But in general, this is not desirable, right? You will want to say that classes that are there is no idea of closeness between classes, right? So the certain elements has to be categorized in a certain class, and you cannot categorize some intermediate value in a meaningful way. Okay. If we are doing this predicting label instead of sort of continuous values, then we go from the regression problem to the classification problem. And the idea is that the goal is to attempt the classification in the right category, and you will make an equal error if you determine if you will make an equal error if you predict the wrong category. Okay. The motivating example are many, right? So let's say that you have some sort of diagnostic test. So you need to have a 0-1 in order to take a decision as a downstream task. Let's say that you have some sort of test and you have to decide if a person has cancer or not, if it's pregnant or not. Of course, for this downstream task, you have to take action. In order to take action, you need an answer which is either 0 or 1. And why not linear regression? I think I don't have to convince you that you don't need linear regression, because you saw the failure of linear regression when doing classification in the challenge last week. Let's say that again, we have a data set of, this was the credit card data set, right? So you have students of different departments, right? And based on the department, you have to predict how many credit cards they have or whatever budget they had. So here the data set will be the some qualitative variable, for example, right? So maybe the height, the age, and so on. And then you had that one of the variables was a categorical variable. Let's say the concentration, right? So you could have computer science, statistics, languages, or otherwise. Of course, you could argue that there is a geometry of closeness between departments. So you could say that if you predict that a person is 1.5, so in this case, 1 is computer science and 2 is statistics, and 3 is, let's say, sociology. So you could argue that if you predict 1.5 for these variables, you mean that a person is in between computer science and statistics. And if you predict 2.5, you're between statistics and literature. But of course, the geometry of closeness of this category doesn't really reflect on a one-dimensional line, and it doesn't really make sense. So let's say that if you try to use linear regression for this, right, you cannot directly use Y to predict text. So what would you do is that you will imply a certain closeness between the categories, and this ordinal numbering of the elements does not reflect correctly into the prediction, right? And what it makes sense is that the model could be able to predict still predict the category, right? But there will be a fault reasoning of assigning a certain model for a certain prediction, because some output of the models cannot be interpreted, right? Very good. So, of course, we can have multiple categorical variables. The simplest case in which we have a binary response. So in the following, we will just worry about the binary response, and if there is some higher categories, then you guys will be able to see how this is extended to higher number of categories. So the simplest form is when you have a response variable y that only takes value 0 or 1. And again, so here we could use linear regression to predict y directly, and then we could do a threshold. Okay, so we could say that if you are above 0.5 or below 0.5, then what you have is a conversion from 0 to 1. And if we do this, we will have this, right? So let's see that here you have the max heart rate, and here you have whether the person has a heart disease or not. Okay, you already see here that on your data set you have a bunch of zeros and a bunch of ones, and already you notice here something that you will not have observed in a different problem, in a regression problem, which is there are people that have the same max heart rate, and for this fixed value of the max heart rate, some of them will have heart disease and some of them will not have disease. Okay, so first thing to notice here is that we represent the data set over this two-dimensional space. On the left, we have the label. On the y-axis, we have the label. On the x-axis, we have the max heart rate. First thing that we notice that when we represent the data set over this plot, people that have a certain max heart rate, some of them have a heart disease, some of them do not have the heart disease. Good. Next, we build a linear model that looks at the max heart rate and tries to decide whether a person has a heart disease or not. But we're using a linear model for this, so this is going to be aligned, right? Then we're going to say, well, the prediction of the linear model will be converted into a binary label just by threshold. So we're going to say, well, we're going to say that a continuous value is a certain probability that you have a heart disease or not. And then we're going to do a threshold. And if you're below this threshold, you have a heart disease. And if you're above, you don't have it. Very tough now to move on with this, right? Because the main issues that we have is that we don't have an interpretation of this. Since multiple people have the same max heart rate, and some of them have a heart disease and some of them they don't, what we really want to model is a certain probability that a person has a heart disease given the heart rate. Okay, so it's clear that we want to describe a likelihood of an event rather than a scalar value itself. Okay, we would like this number that we predict to be between 0 and 1, so that then we can interpret this as a likelihood. And we can try to match the density of the points that we have with the prediction that we have, right? We're going to say, well, for this max heart rate, we're going to have this fraction that has the heart disease and this fraction that doesn't. And as we do this for multiple variables, we have the hope that our model will be able to correctly predict the probability of a heart disease given a certain observation. Okay, so here we have the idea of a probability. Binary response to logistic regression. It's clear that what we want to do is as follows. We want to take a prediction that comes from a linear model, a prediction that comes from a linear model and sort of squeeze it into a probability space between 0 and 1. Okay, so if somebody tells you that you have to do this job, or taking a linear prediction and turn it into what we'll call a sigmoid, right? Turn it into an S-shaped curve that goes between 0 and +1, so that you can interpret this as a probability. You know that you have few ways of doing this. And one way of doing this is this beautiful formula here, which is 1 over 1 plus e to the minus the linear curve. Okay. You guys might have seen this in different contexts. Some people call this a sigmoid. This is, of course, also related to the Cauchy distribution. Doesn't matter now at the stage here. It is clear what we're doing now, right? We're saying we're sort of saying this. Our prediction, I want it to be between 0 and 1. So it makes sense for me to embed it into an exponential. Okay? The exponential will go between 1 and 0. So this will give me a exponentially decreasing behavior when B1 is positive. That goes between 0 and 1. But of course, if you go back to this, right, you don't want an exponentially decreasing behavior. Okay, you want an S-shaped curve, right? So how do you do this trickery? You do 1 over 1 plus. Okay, so that with the 1 over, right, you convert whatever is the denominator between 0 and 1. Okay, then you have this 1 plus, right, that sort of shifts this mean value, right, at 1 plus some linear value, and the rest, I mean, the rest you understand, right? So the rest gives you what you desire. Very good. So the idea is that we do a linear prediction, and then we manipulate this linear prediction so that we have an S-shaped curve that goes between 0 and 1. The idea is as follows. If you look at the, let's say, Taylor expansion of this sigmoid function, you will see that the B0, right, corresponds to the first term of the Taylor expansion, to the constant term, and this will give you that the constant term, which is C equal to minus B0 over B1. So B0 shifts the curve right or left in general, right? And B1 control how steep the S curve is, right? So that, of course, if you see here, right? So if B is equal to 0, then we have something trivial, you have 1/2. Otherwise, sorry, you have just a constant over X. And otherwise, you know, as B1 grows large, then you get sharper and sharper. And again, if you use this Taylor expansion to get some sort of linear approximation around 0 of this behavior, you will have that the distance from 1/2 to almost 1 or 1/2. Sorry, the distance between 1/2. Yeah, this is the 1/2. Okay, to the distance between 1/2 to almost 1, and the distance from 1/2 to almost 0 is related to 2 over B1. So as B1 grows, this distance becomes shorter, so that the S becomes sharper. Okay, so here you see that the distance, for example, is roughly 100, right? So you can, so no. It's too short of a scale. Let's say that this is roughly 10, right? So you can say that B must be equal to almost 20, roughly, right? So B1 is, notice the change of sign, right? So if B1 is positive, then the curve goes from P1 from 0, P1, P of Y1 being equal to 0 to P of Y1 being equal to 1. And otherwise it's flipped around, right? So usually the S goes like this, and if the B1 is negative, you switch the label zeros and 1, right? So not a big deal. Just remember that you have to choose the mapping of the Y between 0 and 1 in a sense that, in a way that it makes sense, right? So for example, if you want a certain prediction of B1 positive, you might have to switch the meaning of the label 0. Good, so this is the plot for you. So you see here that this is the S curve. What you do is that you do a Taylor expansion. Here you have your friend 1/2. So this is when the model is completely uncertain between the two options, the two labels, 0 and 1. Then you have the slope here. The distance here, as we said, this is minus B0 over B1. This is the mean of the value, so where the 1/2 falls. And this is the slope, right? So which we say is T over B1, and the angle is equal to B1 over 4. Okay, so remember this plotting, and remember that here the B1 is positive, so we start from 0, we go to 1. If the B1 is negative, then we will flip it. Okay, good. So when you see this this slope function, right? So then you have to imagine a little bit what is the probability meaning of this. So we have to spend some time discussing probabilities. If you remember the first class that you take in probability theory, often, right, the professor does a little bit of history of probability. I know that I do this with my students when I teach probability. And usually you do this, right? You say, well, originally people try to build probability using odds. And the odds, they come from, let's say, these gambling terms, which says the ratio of the positive outcomes versus the negative outcomes. Let's say that you are betting on a certain, let's say you're at the roulette, and you're betting on red versus blue, and then you have that your odds is 1 and 1, right? So you have half of the time you're going to win, half of the time you're going to lose. So this is a odd. Let's say that you bet on the multiple of 10. I don't know how many numbers are in the roulette, but let's say that this is 1/5, right? With 1 odd, you're going to win. With 5 odds, you're going to lose. And then the professor tells you, well, usually we do not like the odds because mathematically they are not satisfactory. You cannot write a nice mathematical formulation of this. What we prefer to do is to look at probability, right? So where you have the number of favorable odds over the total number of odds. This is because then if you sum over the probability, then the sum of the probability will give you 1. Whether if you sum over the odds of winning or losing, you don't get much, right? You will get, let's say, blue divided by yellow plus yellow divided by blue, and there is nowhere there, not much where you can go, right? So the idea is that if you look at the way in which you map your sigmoid to the linear prediction, it's as if you use a linear predictor to predict the odds, but not only the odds, you predict the log odds. So your odds will be a number between 0 and 1. Then if you log it, you go between minus infinity and 0. You just flip that around so that you have a log odd that goes between 0 and you have a minus log odd that goes between 0 and plus infinity. And so it's clear that then if you see that your model is predicting the log odds, then the way in which you obtain the probability from the log odds is exactly this formula, right? So the definition of the sigmoid is related to the linear predictor inside the exponent through this idea of the log odds. And the idea is that the interpretation of this will be that if a unit of change in x is associated with a b1 change in the log odds, right? So that if you have an increase of, let's say, a unity in x, what you do is that you take those fraction of positive outcomes and you just put it in the negative outcome. Okay, so if you need a way to understand or to imagine what is the effect of increasing b1, remember that the unit of change in x is associated with the e to the b1 multiplicative change in the odds of success, which corresponds to the y equal to 1. Okay, so you go back to this interpretation. Very good. Okay, now the tough problem, right? Because we said, well, linear regression, it was nice because we set up everything. And when we set up our problem with the L2 loss and the linear model, there was a marriage of linear algebra and derivatives, right? And we said, well, the solution was this closed form solution. And we had a closed form solution for the linear regression model and then L2 loss. And then I told you, well, be mindful because this is never going to happen again in your life. This is what you're going to learn today. So for linear regression, there doesn't exist a closed form estimation of the b hats from the 2 parameters. Okay, so linear regression was a gift to us, and this gift does not replicate itself over logistic regression. Okay, so of course, if some of you will want to go and figure out if there is another classification approach in which you choose a different class of model and a different ways of calculating the performance of the model that gives a closed form solution, you will probably win a Nobel Prize, let's be honest. But I think people tried for a long time to come up with a classification model that had these properties and never ever succeeded. And what do we mean here, right? So when we take a linear regression, which shows a loss function as the L2 for loss function, and there was a probabilistic interpretation of on linear regression using Gaussian kernels, and you can show that doing linear regression on a Gaussian kernel will correspond to some estimation of some conditional estimations, and this is linked to linear regression. For logistic regression, you could have a log likelihood approach of estimating the parameters of the coefficients. Okay, so let's say this. So let's say that you have a certain probability mass function that only has two weights, right? So you have a P of y equal to 1 equal to P of y equal to 0 equal to 1 minus P. A way to write this compactly is to write P of big Y equal to small y is equal to P to the small y, 1 minus P, 1 minus y, right? Because if y is equal to 1, one exponent becomes 0, and we get the P. If the y is equal to 0, then P to the 0 is equal to 1, and you just get 1 minus P. Very good. Okay, so this is a this is a way of writing the PMF using a continuous model. Okay, good. Then we put our linear predictor inside there using a sigmoid. So now we can say that we're going to say that the model is related to the features in the following way. Our P is obtained as 1 over 1 plus e to the minus b0 plus b1x. Okay, so we have chosen a way in which the labels are produced. So a label is a certain, there is not a deterministic output, but there is a probability that the label is going to be equal to 0 to 1. The probability of the label being equal to 0 to 1 is what depends on the feature using this sigmoid, which is inside a kernel. So when you have a certain set of features, you use that to obtain the P, and then in a sense you draw a random outcome. This random outcome is going to give you a percentage, a certain fraction of outcome is 0 and outcome is 1, and you say that the fraction is controlled by the parameter P. Very good. Okay, let's move on from this. We want to set this in a framework where we can have a loss. We say, well, we have a true model. We have a model with an estimated P, and I want to make the two models to perform similarly to each other. So I'm going to have an idea of choosing the parameters of the model optimally, so that I can, in a sense, I can reproduce my observation, right? The likelihood of a certain label being 0 or 1. Okay. So what we do is this, right? So we write the log likelihood of a single observation given x and y. So we say, I look at my y's, right? What is the value of y if I observe yi? So the P of yi equal to y is equal to pi yi, 1 minus pi, 1 minus yi. Okay, it'll assume that all the observations in my dataset are independent. Now I can ask myself, what is the likelihood that the parameter P was equal to a certain P, given that I observed the yi equal to y. So now I have a data set of observation, and let's say I have n of those. So for all of this observation, the probability that yi equal to the big yi is equal to small yi is equal to the probability above. So I take the product of this, and I get the probability that P is equal to P, given my observation, is this product here. Okay, we don't like products because they just complicate our lives. We much prefer summations. So what we do is we just take the log of this term. Okay, so this operation is a one-to-one. I have to put a minus in front so that it's increasing in the right way, right? It has the right slope for me. So I take minus log of P of y given y, and then I transported the log inside the formula. So the multiplication becomes a summation, the product becomes a pi, and the exponent becomes a multiplication. So now I have the log of the probability that P is equal to P given my observation y, given my n observation y, is the summation over the yi of the summation over the y of the yi log of pi plus 1 minus yi log 1 minus pi. So far, so good. Nothing strange here. Then I want to say this. I choose a P. I see whether the fraction of labels being equal to 0 to 1 is controlled as of this P. And now this P, I predicted using a linear model and a sigmoid. Okay, so now I want to say I have a certain probability controlled by my linear kernel. And now I want to have that if my labels are mostly zeros and my P is close to 0, then I'm happy. And if my labels are mostly close to 1 and my P is close to 1, then I'm also happy. Okay? So now I want to measure the distance between my prediction and my observation in a way that reflects the fact that my model is not deterministic, but is producing a probability. I would like to convince you, right, that this is the correct loss to take. Okay, so here our input features are the xi's. The parameters are the b0 and the b1. Okay, so if this number is close to 0, then most of the yi's are going to be close to 0, and I have a contribution 0 to my loss function when my label is 0 and my p is small, and I sum over the I in n. If the p is large and I have mostly ones, then I'm going to have a contribution 0 to the summation when the label is 1 and my p is close to 1. When does my loss increases? When my yi is equal to 1 and my p is large. So I have a contribution of the loss when my features predict with high confidence that the y is going to be equal to 1, but I observe a y1 which is equal to 0. And same things if I flip. If my models have a p which is small, so I should have a lot of 0 in my y's, but I obtain a y which is equal to 0. Okay? So it takes a while to convince yourself that this is correct. And what I can tell you to focus on is the following. For as the xi's vary along your data set, right? You're going to have different values of pi, and you're going to have different values of yi. So the first thing that you have to convince yourself is that in your data set, you're going to have many different entries that have the same xi. Okay, so imagine this. In the data set, you have many values xi that are the same. So your features are all equal to the same. Okay, so take all the data set entries that have the same p, the same x1 to xp, and then look at the yi's and see how many of these yi's are equal to 0 or equal to 1. This is a fraction, right? And this related to the probability that the yi is equal to 1, okay? Then what you do is that you are trying to match for those features that are same for your dataset entries, the fraction of 0 and 1s in the label, okay? So don't make the following mistake. So I'll tell you so you avoid the mistake. So I'll tell you what you shouldn't think. For each xi, I get a p, and then here I just have one dataset entry for each yi. Okay, so if the xi are all unique, then this value is either 0 or 1, and so I just have one contribution for this. This is not the case, okay? Because if that's were the case, then it will not be very interesting. The case is interesting because you have an ambiguity in your prediction, meaning that for the same input features, you see the labels switching between 0 and 1s. So you cannot deterministically predict your outputs. What you can do is that you can produce a P that predicts the fraction of 1s and 0s in your labels for a given input feature. Okay? Good. Okay, so now that I try to convince you that this is the correct loss function, then you can ask yourself, wow, I see things that I don't like. Specifically, I don't like the log of 1 plus e to the power of something, because it looks very nasty. because when I take my derivative, right, I know that this is not going to be a good number, right? I know that I cannot do this the easy way, and forget about doing this as a in the vector space, right? So how can I do this? The idea is that you will need some algorithm that does this job very efficiently. Let's see if we are happy with this, right? Because basically, once we have trained the model, right, we have the max HR, and what our model is predicting is, you see the fraction of points that correspond to 0 and 1 in this model. So we see that once we have trained the model, the sigmoid is going to start at 1, is going to stay at 1 if the max heart rate is very low to 0. Of course, if you are half dead, your max rate is, your heart rate is very low. So the model should see mostly labels that are equal to 1. If your heart rate is very healthy, you have a very high, you have a young person, you have a very high max heart rate, then the probability that you have a heart disease is very low. So your model predicts that very few people with a large max heart rate have a heart disease. And in between this, you have a nice and smooth transition of this probability. So even if the prediction was a hard prediction, we embedded into this hard prediction a smooth model, a smooth S that gently transition from the phase in which you have a high certainty that the person has heart disease to a high certainty that the person does not have a heart disease. Good. So there are different ways in which you can fit a linear regression model. A logistic regression model. So you just go into sklearn, you take a logistic regression, which is in the linear model package, and you can put in your coefficients, and you will get an estimate for the beta 1 and the beta 0. Notice that the beta 1 here is negative because we are doing this flipping, right? So we are starting from the p equal to 1, we're going to the p equal to 0 instead of the opposite. If you wanted to have a positive p, you just flip the meaning of the 0 and 1 levels. Good. So then you can do some exercises for yourself. You can write down the logistic regression model. You can write an interpretation of B1, and you can see the probability of a heart disease with somebody with a certain heart rate. And then you can also ask yourself, if you were using this purely for classification, how would you use so? Then you will have to do some digitalization of the variables. Okay. Good. Guys, let's do 10 more minutes, then we stop. We will stop here. Very good. Okay, we're here. Like in linear regression, when the prediction X is binary, then the interpretation is simple. As always. When you have more values X, then you will do is that you will need to have a larger linear model that you embed into your sigmoid. So, for example, if we have that with a categorical variable X equal to 0, X equal to 1 to relate the prediction in the prediction model for the heart disease, then we could interpret the parameter B0 and B1 as the probability, as some sort of indicator of the influence of the sex over the heart disease, right? So you will say that you will say that let's say if 26%, what was the data here? So 26% of women has a heart disease and 55% of men has heart disease. So a priori, we know this, right? We know P of Y1 equal to 1 given an X is equal to 0. So you have a heart disease given that you're a female is 0.26. P of Y1, P of Y equal to 1 given X equal to 1 is 0.55. Then we do the log odds, right? We said that the log odds are equal to this B0 plus B1, and then we can interpret this as follows, right? So the P of Y1 equal to 1 is a summation of X0, X1, so this will be a 1/2 and 1/2. And yeah, and we can mathematically see what is the influence of being a male over the probability of a heart attack, and you will see that this is reflected in the model. As always, right, we want to have a certain uncertainty on the estimate B0 and B1. And you can use this to build confidence intervals. So the estimation, the estimation for the standard errors of these estimates, likelihood-based estimates, is based on the Fisher information. Some of you will study the Fisher information when you do estimation theory. I don't know if you're going to take a class. It's a very important concept. It's the inverse of submatrix. It's very important. And it's related to the curvature of the log function. There is an underlying assumption that there is a Bernoulli distribution that controls the y's. So there is an independence between the outcomes. And there is a same parameter P1 that controls the labels being equal to 0 or 1 for a fixed input feature. And so this means that one can use a Gaussian approximation of this problem, and so that you can use this Gaussian approximation for doing inference and for obtaining confidence intervals. And you can also do bootstrapping for obtaining some confidence interval of this. Okay, so if you go through this, for example, this is an example of the max rate and the heart disease, where you do logistic regression. You have the number of iteration, the residuals, the log likelihood, and this is what you want, right? The coefficient P0 and P1, the standard error, right? So you see the error on the coefficients, and then you have the F1 values, and so on and so forth. Good. Let's stop here for now, guys. Okay, let's stop here. Let's do 2 more slides, guys, and we stop. So then classification using the logistic model, that's very easy. So remember that in our model, right, we would like to have a prediction which did a binary, which is either 0 or 1. And of course, the way in which you binarize the output of the model is just to see if you are greater than 0.5 or smaller than 0.5. Okay, so this is very simple. So this is called a Bayes classifier. Because the Bayes classifier assigns the label of the most likely class. Right? So here you're saying that the class 0 has a higher likelihood than the class 1 when P0 is less than 0. When the P hat is less than 0.5, and so you do this, and we call this Bayes classifier. So sometimes people say naive Bayes with respect to this decision. When is the Bayes classifier a good classifier, and when is a Bayes classifier? It's a question that you guys already partially answered with the asteroid dataset, because with the asteroid dataset you understood the issue with the number of representatives of a certain class, correct? So the Bayes classifier minimizes the overall classification error. There is, it classifies the summation 1 over n, summation of yi different than yi hat. Is this a good loss function to minimize? Yes or no? Of course, you have this one here for each of the. So these yi's can belong to one of the 2 binary classes. You can also extend this to more classes, and you will see then the issue of the number of elements per class, right? So if most of the time the yi's are equal to 0 and you just have a very few ones, then of course the sensitivity of the ones in this formula is not great. You will want to balance the yi's, have a per class balance, right? So normalize the summation over the different classes. And this is something that I think some of you already thought about. And how do you extend this when you have multiple categories? As we said, no problem, just using indicator function. Okay, good. So now next time we do multiple logistic regression, it shouldn't be too much of a surprise for you guys. I think we stop class here. Everybody should be happy. The recording will be available after class. So let me stop the recording, and then you let me know if you have any questions. Otherwise, I'll see you next time.